So this is a collaboration with Scott Hsieh of Mayo Clinic and myself, and I really appreciate the work. Disclosure from both of us, and okay. In the pointer. Okay. I appreciate the discussion with Shalini. So we are talking about the pulse pileup on the photon counting detector in this talk. And we're going to review the current scheme that Peter Noel reviewed, the threshold subtraction method, and propose a new method. And then talk about Monte Carlo simulation to evaluate both of these performances, and then actually the statistical model, agreement with the statistical model, and so on. So on the left, you see that pulse pileup, that when the quasi coincidence photon incident onto the detector, that may create integrated pulse observed by one pulse with higher energy than the originals. And that's the main topic of this today's talk. As a side note, there's an additional effect that is called charge sharing or K-escape effect. That is nothing to do with the count rate. It happens all the time. And that is when the photon is incident onto the detector between the anode or close to the boundary, that incident energy may be split into multiple pixels, and charge is shared, energy is shared, number of photons increased, double counting at the lower energy. And you see this effect a little bit, but main focus is this pulse pileup effect. So this is the current standard detection circuitry, the pulse coming from the left, and the pulse shaped, and the height of the pulse is compared to this energy threshold set in there, such that this T1 counts the number of up-crossing events of the set threshold, 1, 2, 3, and so on. The threshold 2 would observe that up-crossing events against this E2 get 1, 2, 3, 4 counts. One count here and no count. After the data acquisition is done, you read out the data and subtract the output from adjacent energy threshold to try to get a number of photons such as this observed within this energy window. But notice here that subtraction for this bin 1 goes negative. That is because that this measurement happens before this pulse comes down to the baseline level. In other words, that pulse at the baseline fluctuates depending on the pulse pileup or count rate. So that happens. Also, that if you try to see the number of photons that are incident onto the detector, which is 5 photons, there's nowhere near that, or even this one. So you lose some of the accuracy in addition to some of the effect of the fluctuation. And these measurements, as you see later on, do not agree with the statistical model that are developed by prior researchers. So this is a scheme that we're going to propose, the direct binning scheme. Nothing changed major. Only we are adding this local operation that observes the output of these 2 adjacent thresholds, and add the count to this counter only when the upper threshold is not observing the pulse. So when this happens, that the upper threshold is not observing the pulse, so this would count it as one count in bin 1. But this pulse rising, crossing this point, but closely, it will pass that next pulse, the threshold, such that this energy window is responsible for this pulse. This is not, so it's not going to be counted. Similarly, this pulse is not going to be counted as a count for the bin 2, and only this one is responsible for that. This is not the active pulse peak detection, right? Pulse peak detection is known to be very, very noisy, so we're not doing it. Instead, what we are doing is a simple local communication between adjacent threshold, such that we are effectively counting some peak within the threshold energies. So compared to the results of the DB scheme that I expected from this pulse train, that we are measuring the pulse peak accurately. But again, it's not the active purpose. All right. So the purpose of this study is to assess the performance of the direct binning scheme and this threshold subtraction schemes, and assess the agreement with statistical models. Because if we want to use any statistical information embedded in the data needs to agree with the statistical model we're going to use for the algorithms. So we started with the Monte Carlo simulations, and the data were generated for the cadmium light detector, this configuration, and focused on 4x4 pixels. Pulse width was a reasonable pulse, not a triangle pulse or anything like that. We had 4 thresholds, and we changed the tube current from 1 mA all the way to 2000 mA at the fixed MAS levels. The data are processed to compute the 4x4 pixels, and we computed the current rate curves, Kramer lower bounds for 3 spectral tasks, but we only show waterborne material decomposition results today for the sake of simplicity. We also measure the mean variance and covariance of the Monte Carlo data and compare those with a statistical model. So what are the statistical model we used? We used a non-parallelizable detection statistical model, and expectation was derived long time ago, and the variance was measured, quantified this way by Yu and Svesler. So M naught is the input, A is a relative input count rate, tau is the speed of the detector at that time, and we can compute the expectation and variance this way, right? Adam Wang derived this measurement-based mean variance covariance of the bin data about 10 years ago, and we're going to use it. Just to make a shortcut, that the probability of bin incident onto particular bin I was computed based on the measurement. So we don't rely on that statistical model of that prediction part. We started with this BI obtained from the measurement itself and computed the variance and covariance this way. Limitations of this the model is that that simple detection scheme is assumed, which is not the case for all the simulations. The pulse shape was supposed to be bin pulse, so finite width is not allowed. There's no baseline shift, baseline fluctuation in the model such that this effect of the tail propagated into the succeeding pulses. None of that is involved. There's no charge sharing, even if the count rate is low. Well, when the count rate is low, that all the photons are supposed to be independent, right? But by going through the double counting in the charge sharing and sum up to the 4x4 pixels, we have a lot of double counting so that the statistics are not Poisson distributed. But nonetheless, it's not included in the model. So there are certain limitations, but probably that's the best statistical model available for us. So let's use it. This is the first results, the count rate curve. And you can see that the dB, that the direct binning goes to the higher count rate compared to that the threshold subtraction scheme that are saturated here and goes down. If we compare the peak count rates, the dB goes to 350 the million counts per second per square millimeter, which is about 59% higher than the TS scheme. The tube current value achieved at the peak is the 1200 milliamps for the dB compared to 600 mA for the TS. So dB improved at the count rate or tube current range usable until the saturation by a factor of 100%, which is a good improvement. But how about the spectral performance? So we calculated the normalized Kramer lower bound against the tube current value and normalized it by the value of the 1 mA. At the 1 mA, both of these detectors behaved in the same way, so it's normalized in the same way. And you can see that both of these detection schemes got peaked out and comes down. By the way, this is a Kramer lower bound, so the lower the better. So degrades the noise performance as we increase the pulse pileup and come down. And if we compare these two, and take a ratio of the Caramello lower bounds, you see that a dB always has a lower noise than the TS up until this point and bottom out and come back this way. Because this is the point that the dB hasn't hit the peak yet, but the TS started coming down. But considering that this is a range that we're going to use this detector anyway, that there's up to 30% noise reduction using this dB scheme. Okay, so that's the merit of this detection scheme. How about the agreement with the statistical model? Right. On the left is dB, on the right is TS, and we see that the expectation and variance of the total counts in here. And you can see that expectation agreed with this model quite well. While in variance data, in that Monte Carlo data in the circles, markers, that variance in the lower count rate is quite larger than the model, but gradually it agreed. The reason for this disagreement is that at the lower count rate, that charge sharing is a dominating factor for the noise performance, and then model not having the charge sharing effect, while the Monte Carlo data definitely has that effect, resulted in this underestimation of that noise and so on. Same is true with the TS scheme, that the expectation of the counts is nicely agreed to that model, while this variance estimation is different, so that it doesn't agree with the statistical model when the count rates are low, but it started gradually increasing the agreement quite well. Now, the challenge is that the statistics of the bin data, and on the left again is dB, on the right is TS, and let's focus on bin 1. Markers are Monte Carlo data, and then dashed 1 is a model. You see the disagreement in here because of the charge sharing again. But as we increase the count rate, pulse parallel becoming a little more dominating factor, and then model and the data agreed quite well. For the bin 2 in the red, the disagreement is smaller to begin with, and then throughout the count rate range, agreement is good. And so was bin 3, blue, and bin 4 in magenta. Nice agreement between the actual Monte Carlo data and the statistical model. In contrast, if you take a look at this right plot, that the disagreement is obvious when the count rate is low for the bin 1, and then the Monte Carlo data goes this way, while the statistical model predicts this performance. So there's a very large disagreement between the model and the data, and that can be observed with the bin 2 in the red as well, the discrepancy between them. And bin 3 and bin 4 have a reasonable agreement, but not as good as the dB. In the last slide, I'm going to show you this covariance between energy windows, so that the covariance between bin 1 and 2 had, again, that larger value when the count rates are low, because that dominating noise factor charge sharing is not included in the statistical model. But as the qualitative change of this behavior going down and go up can be in a good qualitative agreement with the statistical model. If you take a look at the covariance between bin 1 and 3 red, or 1 and 4 in blue, you see that there's a decent agreement between the statistical model and Monte Carlo data. So dB behaves close to what the statistics is expected to show. In contrast, in TS, in short, you can see that the model prediction goes this way, going up, while the Monte Carlo data showed the covariance in a larger magnitude and sometimes in an opposite sign and so on, like blue. Right. So it shows that it's very tricky to characterize the behavior of the TS model detection scheme by using a current statistical model. So in short, that in our opinion, that a dB is better than TS schemes because it had a 59% higher maximum count rates and up to 100% larger tube current range usable. It had a 30% beta thermal lower bound in the waterborne material decomposition, and had a better agreements with statistical models for variance and covariance of the beam data. Both that DB and TS scheme had a larger variance than the models for lower count rates because of this missing piece of the charge sharing. And it would be desirable in the future to derive a statistical model that includes the charge sharing such that we can fully characterize that noise statistics with charge sharing and with pulse pileup effect. The effect of the baseline restorator is not included in this model nor the simulation, but it seems, so it could be a future work to include this effect in the simulation. I think that the good agreement, even without the baseline restorator, showed that if combined with the baseline restorator, possibly that DB would behave even better, although that TS agreement may improve as well. But it all depends on the goodness of this baseline restorator, how much of the noise it would add and bias it would add and so on. So yeah, so that's all. Thanks for your attention.
Right. The paper is open for discussion. Thanks for the interesting talk, Ken.
Thank you.
So maybe you said it, but I didn't quite catch it. Is this DB scheme enough to remove the negative count problem altogether? Or because I would have expected that you would need some logic that takes all the bins into account to really assign the right bin to each event. But are you saying that it's enough to let two adjacent bins communicate with each other in this case, and you don't need sort of wires from every bin to every other bin?
Correct. We only need to communicate between the adjacent energy thresholds, and that would get rid of negative counts because we don't have to do the subtraction. And this communication would take care of the difference between these two bins.
Okay, thanks.
Nice work, Ken.
Thank
Just
you.
to follow up, so when you have those pound signals for the lower energy bins, and then you have the and, how wide of a time window do you leave that open?
Right. Good question. So in this experiment, we used half of this pulse duration as a coincidence time window, which is 10 nanoseconds. It could be shorter because we are only seeing a part of this rising peak. It could be as short as like 5 nanoseconds or so. Right.
Thanks.
Thank you.
So I have a question if nobody else does.
Yeah.
So this simulation is for 4 energy bins, and I wonder if you can say anything about what happens if you look at fewer or more energy bins.
Right. I think that fewer energy bins would make the situation worse for TS because there are more cases that baseline fluctuation would fluctuate within the energy window, and that would mess up the counts. For the more windows, that's a good question. I can't picture that right now.
Okay, thank you.
Thank you. Thanks.
Yeah, King, very nice talk. I
Thank you.
enjoyed the slides. You explained the things.
Thank you.
I'm just curious. You're talking about noise, obviously is important. You're talking about the right noise model. So what is the right noise model, and what does that impact in the end? What?
Right. So right noise model is to compute the expected variance covariance of the data, right? And the merit of having a good statistical model is to use it in the inversion process. You know, the inverse problem can be more accurately solved or more precisely solved.
So
because-
you're saying maximum likelihood inverse.
Right.
Does that,
There are many ways to use the statistics, but maximum likelihood is a great example.
okay.
So that having not having a data model mismatch would be critical to
I
get the
see.
best
But
results.
I'm not sure about that in terms of later parts of the chain or recon processing, you know. Anyway, we can
Right.
talk about
So
that.
depending on that, the succeeding process method itself, that the value of having a statistical model may not be valuable, may not be critical, but it is in a way that wasting information that we could use in the succeeding algorithm.
Agree.
So yeah,
Thank you.
thank you.
Let's thank the speaker again.
Thank you.